me? Are you able to hear me?
Yes, ma'am.
Okay, so let me just start. So this is the next chapter, chapter number 33. In chapter number 32, we have actually seen how a moving charge can be affected by a magnetic field. You didn't care about what produced the magnetic field. You didn't bother about the source of the magnetic field. All you knew was there is a magnetic field. When there was a charge moving in that region, it experienced a force. Based on that, we had 5 applications. And then we talked about something that is slightly more complex. We didn't want to stop with only one single moving charge. We talked about a series of moving charges. And series of moving charges was simply current. Okay, then we saw that a current carrying conductor in a magnetic field can experience a force. And then we saw that a loop in an external magnetic field, a current loop in an external magnetic field will experience zero net force, but then there can be a torque. So these are what you have done in chapter number 32. But coming to chapter number 33, here we are going to bother about the source of the magnetic field. Chapter number 32 was the effect of the magnetic field on a charge or current. Now, chapter number 33 is the source of magnetic field. What can be the source of magnetic field? Okay, we are going to see that a single moving charge can be a source of a magnetic field. Then we are going to see that a current can be a source of a magnetic field. Then we are going to see different configurations of currents and what is the corresponding magnetic field. And finally, we will end up all this with Ampere's law. Ampere's law is going to be a very simple way in which we are able to get the expression for the magnetic field due to various current configuration. Now, to draw an analogy, I would like you to go back to electrostatics. In the chapter number 26, we have seen electric field, and we have seen that static charge can be a source of electric field. After that, we saw a collection of static charges, like for example, a line of charge. Then we saw a ring of charge. We saw a disk of charge, and we got the equations for the electric field because of each of these charge configurations. We talked about dipole also there. Then after that, we went to Gauss law. Gauss law simply made our job. All this was very complicated mathematics. A lot of calculus was there. But then when we went to Gauss law, we just used the symmetry of the charge distribution and symmetry of the electric field, and then very easily arrived at the expression for the electric field due to various charge configuration. So please understand, Gauss law there is analogous to Ampere's law that we are going to see in this particular chapter. Okay, so whatever I have said is already summed up here. So moving charges can be a source of magnetic field. Moving charges can be affected by magnetic field, which means two sets of moving charges can influence each other. Okay, so that's the reason why two current carrying conductors can either experience an attractive force or a repulsive force, depending on whether the currents are parallel or anti-parallel. It comes from here. Okay, so objective also I've already explained. So I think we can move to the next slide. Okay, so what's the first signal that currents can give rise to magnetic field? So you have this Oester's experiment where you can see the first picture. There is a current in a wire. There's a current in a wire. And let's say you're having a plane like this fitted. And then if you put a compass, you're going to see that the compass is going to experience a deflection. The red part of the arrow is the north pole and the other one is the south pole. So you're seeing that the compass, magnetic compass, will experience a deflection, and you're going to see that, you can, as you go around in a circle, you can see that the red arrow is facing in a certain direction. Okay, so that means something. That means that the direction of the magnetic field direction is always taken as the direction towards in which the north of a compass is pointing. So you'll find that magnetic field lines are going to form closed loops around a current carrying conductor. So this is the first proof that a current can be a source of magnetic field. Then of course, go to the next picture. There you have Rowland's experiment. In Rowland's experiment, what is done is you are going to have a gold plate charged, and then you're going to revolve this plate. When you revolve this plate, what happens is this charge starts moving. The charge starts moving, and then when you get a magnetic compass near it, you're seeing that the magnetic compass is going to experience a deflection. So once again, you're understanding that here you are having a charged body which is moving. When the body is moving, the charge is also moving, and it is giving rise to a magnetic field. So essentially, you come to the conclusion that moving charge creates magnetic field, current creates magnetic field. Okay, so once more, like what happened in the last chapter, like what we did in the last chapter, here also we have a thought experiment. A thought experiment is something that you can't really do in a laboratory. You cannot do it in a laboratory, but then you can actually presume that if you do this experiment, these are going to be the outcomes. And based on those outcomes, you're going to hypothesize something. Okay, so and then extend it to a bigger situation which can be experimentally tested. Okay, so that's a thought experiment. So first condition is this thought experiment is going to be done in a place. You're going to do it in a place where there is a charge, and the charge is going to move with non-relativistic speed. Non-relativistic speed means the speed of the charge is going to be much less than the speed of light. Okay. You need to put this condition because when you go to relativistic speeds, mass is not a constant, mass will change. We don't want that complication. So we take a velocity which is much less than the speed of light. And then you're going to conduct this experiment in a region of Earth where the Earth's magnetic field is negligible. You will ask, how do I do an experiment in a place so that the Earth's magnetic field is negligible? You know that the Earth's magnetic field is lying along the north-south. Earth is a magnet. Okay, and we have also seen that FB is equal to QV cross B. So if you have a charge moving parallel or anti-parallel, then this Earth's magnetic field will not affect your charge. So that's the way you can get rid of the Earth's magnetic field. And then you're also going to do it in a place where the electric field is zero. You don't want interference from electric field. Then you will ask, how do I do an experiment and ensure that the electric field is not there? You can do it. You just conduct this experiment inside a metallic conductor. Inside a conductor. If you do it inside a metallic conductor, what happens is the hollow of the metallic conductor, because of Faraday's effect, okay, it's called a Faraday cage. So electric fields cannot enter. So you can ensure that nothing is going to give rise to an electric field and spoil your experiment. I hope these initial conditions are clear, guys.
Yes, ma'am.
Right. So now what we do is, and we also want to make our life simple, we will take a point charge, a charge which is positive. Positive means then you don't have to have this hassle of dealing with a negative minus symbol. So let's consider a positive charge and allow it to move as seen here. Okay, allow this charge to move with a velocity v. Okay, when you do that, what happens is you are actually, or let me go to the next slide and explain. What are you going to see? What kind of magnetic field? Magnetic field, of course, you can measure hypothetically. You want to measure using some device, let's say. Okay, so what is the property of the magnetic field that you are seeing? Let us say. You are seeing that the magnetic field that you are getting, the magnetic field is directly proportional to the magnitude of the velocity. B is proportional to the velocity of the moving charge. The moving charge is producing a magnetic field, and the value of the magnetic field is proportional to the velocity. If I increase the velocity, I'm getting a larger magnetic field. And similarly, you're also finding that the magnetic field that you're getting is proportional to the charge of the charge particle. Instead of doing this experiment with a proton, if you were to do it with, let's say, a helium positive ion or helium positive ion, then you find that the magnetic field is double. Okay, so you are seeing that the magnetic field is also proportional to the charge. But the next thing that you are noticing is that if you see how this magnetic field is related to the velocity, what happens is first you're doing this experiment with the magnetic field moving in this direction. If you reverse the magnetic field direction, if you reverse the velocity of the charge particle, then you're finding that the direction of the magnetic field is getting reversed. Similarly, instead of doing this experiment with a proton, if you do this experiment with an electron, then also you find that the direction of the magnetic field is changing. Or in other words, you are seeing that magnetic field is influenced by, what are the two things? Influenced by the direction of velocity. It's influenced by the direction of velocity and it is influenced by the sign of the charge. Please, each of these things which I'm writing, no, we are going to put them all together later. Then, finally, what is the third thing that you're noticing? The third thing you're noticing is that I have some Gauss meter, which I presume can measure this field. Now, if I put that, say I have my charge particle which is moving in a straight line like this. If I put my Gauss meter anywhere on this line, either behind or in front, anywhere on the line of the velocity or along the motion of the charge particle, either behind or in front, if you put a measuring device and find the magnetic field, we are finding that the magnetic field is 0. At all other points, there is magnetic field, but then on the line of the moving charge particle, if you take a point in front or behind, there is no magnetic field. Okay, so these are the 3 observations that are made. Then let's go ahead and see if there is something more. Yeah, then another very interesting thing that you're noticing is that, let me just copy this picture, take it to the next page also. Okay, another interesting thing that is observed is that this is the line of motion of the charge. I can actually see circles around it, circles perpendicular to the line. I can actually see a number of circles. I can't see the circle. There are actually a number of circles that you can imagine around this line in a plane perpendicular to the velocity. In a plane perpendicular to the velocity, you are able to imagine a number of circles, and at all points on the circle, on any one circle you take, at all points on the circle, you are finding that the magnetic field is tangential to the circle. You're finding that the magnetic field is tangential to that imaginary circle. Just take a circle. This is the path of the charge particle, either in front or behind. You just imagine a circle, and at all points on the circle, you're finding that the magnetic field is tangential to the circle. And what is the direction? You're finding that the direction is of this tangential to a circle means it is moving around in a circle. The magnetic field line is like this. Okay, but then is it like this or is it like this? Is the next question. For that, you use your right hand rule. Put your right hand thumb in the direction of the velocity of the positive charge. Put your right hand in the direction of the velocity of the charge particle. Then your curling finger gives the sense of the rotating magnetic field. Okay, so you're finding that if this is my velocity vector, this becomes by magnetic field, or the magnetic field direction is given by the right hand rule, and you're finding that the magnetic field is always perpendicular to the V vector. It is lying on a plane which is perpendicular to the V vector. And then you'll ask, which plane? You can take any plane. You can take any plane. Okay, and next thing is, what should be the radius of the circle? That will be the next thing that you're going to see. And before that, at any point on that imaginary circle, the magnetic field is tangential is one thing. Next thing is the direction is given by the right hand rule is the next thing. The third thing is the magnitude of the magnetic field is the same at all points on that circle. Okay, so that means magnetic fields are, if this is the line of the moving charge particle, then using your, let's say this is the direction, then using right hand rule, I'm seeing that I can get magnetic field lines which are circular around it, and the direction is given by the right hand rule. And if I take a particular radius and look at what is the magnetic field on that circle, at every point the magnetic field value is the same. Okay, then next thing is, this is for some radius r. Now, if I'm going to increase the radius of the circle, so first I take a circle like this, look at the magnetic field. Then I take a bigger circle. Okay, then what do I see? On the bigger circle also, I'm going to get a right hand rule, I'm going to see a magnetic field, but then the value of the magnitude decreases as 1 by r square. The magnitude decreases as 1 by r square. Now, what is this r? Let us see. R is the distance from the charge to the point on the circle. Like for example, if my charge is here at this instant of time, please remember it's a moving charge. If my charge is here at this instant of time, then my R is going to be this. This is R. Okay, or I will say R is the position vector of some point of interest with respect to that instant where your charge is, or the position of the charge becomes the origin for this vector. The position vector of the point P with respect to the charge. So you're finding that the magnetic field is proportional to 1 by R square. Which means, if I'm going to take a circle somewhere here, the magnetic field is going to be smaller. Okay? And another very interesting thing that you're going to notice is that the magnetic field at some point P varies as sine phi. It varies as sine phi. Let us see what is phi. Phi is the angle between the V vector and the R vector. Angle between the V vector and the R vector. So this one. This is phi. Okay. Now you see here, instead of taking a point P here, if I take a point P here, then accordingly my phi value is going to be different. Or if I take a point here, my phi value is going to be different. Or if I take point here, my phi value is going to be different. So phi is actually the angle between the R vector and your V vector. And then by now I expected somebody to ask me, Madam, this R is also going to change with time? Yes, R is going to change with time because the charge itself is moving. The origin of your vector R is moving. So your R vector also keeps on changing magnitude and direction. So phi also keeps changing. But any instant of time, if you try to look at how the magnetic field will be at some point P, there you can simply say that the magnetic field is going to be proportional to sine phi, where phi is the angle between the V and the R vector. Okay? So we are going to combine all these things. We are going to combine all these things and then arrive at something. Let's see what it is. So once more, I have defined what is R. R is the position vector of the point P. What is point P? Point P is the point where I'm interested in finding the magnetic field. So R is the position vector of point P with respect to the moving charge. Moving charge is the origin. So now, after combining all this, if you try to see how the magnetic field will be, you see here, this is your moving charge. I have a point P here. This is the R vector for that point, for that snapshot moment. This is my V vector. So this is my phi. Now, if I see what is my magnetic field, use the right-hand rule. Use the right-hand rule. Okay, you're seeing that the magnetic field is going to form a circle. The magnetic field is going to form a circle around this line. Okay. It's going to form a circle around this line. And at this point, if I draw a tangent, it's going to be this. So this is the direction of my magnetic field. If I take a point here, the magnetic field is this. If I take a point here, it's going to be here. This will be this. Okay. And here, straight away from this picture, you are able to understand one thing. We are going to see that B is perpendicular to the V vector. B is perpendicular to the R vector. B is simultaneously perpendicular to the V vector and the R vector. Or you can say that B is perpendicular to the plane of V and R. It is perpendicular to the plane of V and R. Perpendicular to the plane of two vectors. Perpendicular to the plane of two vectors can be obtained by taking a cross product. Or you can simply say that the magnetic field is going to be parallel to V cross R. V cross R. And V cross R is VR sine phi. So that's the reason why we got that sine phi also. So now combine everything that you got. Okay. And then write a single equation. So that equation is going to be B is equal to some constant into Q, because B is directly proportional to Q. Next, it is directly proportional to V. It is directly proportional to 1 by R square. Again, I'm repeating. It is directly proportional to Q. It is directly proportional to V. It is inversely proportional to R squared. Or it is directly proportional to 1 by R squared. At the same time, we have seen that magnetic field is perpendicular to V and R. And it is proportional to sine phi. So what you can do here is all those things can be taken in this particular fashion. We can put V cross R. When you put V cross R, we are going to get VR sine phi. But then it is inversely proportional to R square. Because you have an R in the numerator, you have to put a cube R here. So R cube. Okay. Or you can also write it in another way. We can write it is proportional to Q V cross R cap by R square. Anyone? What is R cap? What is R cap? Look at that. R cap by R square. R cap is the unit vector. It's a unit vector parallel to the R vector. Or R cap is R vector divided by modulus of R. It is like your I cap, J cap, and K cap. So once I'm going to do that, then I don't have to put R cube here. I can just put R square. Okay, now you see everything that we discussed will be satisfied by this particular equation. Everything we discussed will be satisfied by this particular equation. B proportional to Q, B proportional to V, B proportional to 1 by R square, V, B perpendicular to V and R simultaneously, B given by the right hand rule, and B proportional to sine phi. Everything is satisfied by this one equation. And this equation also shows that B is a vector. How do I decide that B is a vector? Anyone? Anyone? I know you have 2 tests, but then syllabus also should go on, no? Anyone? Oh, well, then if you're not interested, I'll just go ahead and teach.
Yes, ma'am.
Yeah. What is, how do you know that B is a vector? Can't you see a cross product here? The cross product is telling you that B is a vector. Okay, and then let us just remove that cross. We can write the magnitude of the B vector as K. That constant K has become mu naught by 4 pi, and then Q V R sine phi divided by R squared. So this is finally the equation for the magnetic field in the scalar form. But in the vector form, you have to write what is given inside that box. And what is K? K is mu naught by 4 pi. Anyone? What is mu naught? What is that? Magnetic? What is epsilon naught?
4 into 10 to the power minus.
No, I'm asking what is the word? What is the English word for mu naught? Is it permeability or permittivity? That at least you answer.
Permittivity.
Permittivity. Is everybody agreeing? Anyone opposing that? Okay, so K is equal to mu naught by 4 pi, where mu naught is actually 4 pi into 10 to the power of minus 7. So 4 pi gets cancelled. That's the reason why you get 10 to the power of minus 7. Tesla meter per ampere. Tesla meter per ampere. So that's the unit of K. And what is the unit of magnetic field? Tesla. Okay. And what is the analogous situation that you have studied in electrostatics? The analogous situation that you studied in electrostatics is a steady electric field can be produced by static charges. Here, a magnetic field can be produced by moving charges. So static charge and moving charge, these are the analogous things. Okay, next. What is electrostatics, anyone? What is the difference between electrostatics and electrodynamics? What's electrostatics?
Electrostatic, positively charged particle, and electrodynamic means negatively charged particle.
Stationary.
No, I'm sorry to disappoint you. Or rather, I'm sorry that after 2, 3 months, there's nothing wrong. I'm not laughing at you. I'm not making fun of you. I'm not shaming you. But then I'm sorry that that's the wrong answer. Electrostatic. Static means not moving, not changing with time. Electrostatics are constant electric fields. I have a charge that is not moving. It is at rest. Okay. Now, if I take a point and find what is the electric field because of this charge, that electric field remains a constant in time. As long as this charge is going to sit here, the electric field at that point is going to be that. That is electrostatics. That electric field does not change with time. On the other hand, when that electric field at a point is changing as a function of time, then you get electrodynamics. Okay, so electrostatics was, you had assumed in all our insulators that we took, a line charge, a ring charge, and all that. So it's got nothing to do with positive and negative charge. Electrostatics is the study of electric field produced because of static charges. Electric field can be produced because of moving charges also. Okay, but then moving charge will simultaneously produce magnetic field also. And that electric field and magnetic field are going to be related to each other. But in electrostatics, no magnetic field. It's just a steady, constant electric field at a point. Okay, if you understood this, let me ask you another question. What is magnetostatics? What is magnetostatics? Okay, take the same logic. Electrostatics means a steady electric field at a point that does not change. The value remains static. Okay, so the same logic you can use here. Magnetostatics means a situation where I have a source that is creating a magnetic field. I have a source that is creating some sources there, which is creating a magnetic field at a point. This magnetic field, if it doesn't change as a function of time, then I say that that condition is magnetostatic condition. Okay, now answer this question. I was talking about this positive charge moving with a velocity v, and then I took a point P here. Is this magnetostatic? Is this field static?
No, ma'am.
Why is it not static?
The proton is moving.
Because it's moving. What is going to happen to your r vector? R vector also keeps, at this instant r vector is this. Next instant r vector will be this. This instant angle is this. Next instant the angle is something else. So the magnetic field keeps changing. The magnetic field at a point keeps changing when you're talking about a magnetic field produced by a moving charge. So that is not magnetostatics. Then what is the meaning of magnetostatics? How do you exactly get magnetostatics is the next question. So that let me just try to answer. Please remember the principle of superposition. The principle of superposition is valid for electric field and magnetic field. Okay, so what does that mean? The net field at a point will be the vector sum of the field due to two different sources. The field due to two or more different sources. Okay, so that logic let me take and then think about a series of positive charges in a line. A series of, I'm just drawing a small picture here of let's say 5 or 6 charges. But think of around 10 to the power of 30, 40 charges moving in a line with some speed v. Okay. Now I take a point P here. And please remember this line is going to be very big. It's a very big line. It's going on. Okay. And these charges are all moving. It's a big train. Never-ending train. It goes like this and from behind also it's coming. If I take a point P here and find out what is the magnetic field at this point, by the principle of superposition, the magnetic field at the point P is because of the magnetic field due to each of these individual charges. The magnetic field at the point P is the vector sum of the magnetic field due to each of these point charges. So now, let's say I have 10 to the power of 30 charges contributing. So now, if this fellow moves away, let me say I'm just going to think of a line of this length where all my charges are. So if this fellow goes, another fellow would be coming into the frame. Are you understanding? If one charge goes out of the frame, another charge has come into the frame. So what happens is, even after, let us say, 2 or 3 minutes also, the net charges which are contributing to the magnetic field at that point P remains the same. So essentially what am I getting? I am getting a magnetostatic situation. Did you understand what I'm saying? Yes or no? Should I explain it again?
Oh, no.
No. Okay. So if I am able to have a series of charges which are moving in such a way that one goes away, another takes its place. One goes away, another takes its place. It just keeps on happening. Then I will be able to get a static magnetic field at a point. This is magnetostatics. What is this line of flowing charge called? What's a line of flowing charge? A continuous flow of charges is called current. It's called a current. So if I'm going to have a current that is static, a current that is not changing as a function of time. Let us say I have a 2 ampere current in a wire and it remains 2 ampere. Then because of this 2 ampere current, the magnetic field at a point will remain a constant. It will not change. Okay, so we can simply say that you can produce a steady magnetic field. You can sum up everything by saying that magnetostatic is a production of a steady magnetic field by charges with no change in motion. By charges with no change in motion. If they are all moving with a certain average velocity v, it continues with the same average velocity v. Or indirectly, you must remember J is equal to NEVD. J is equal to NEVD, chapter number 39. Or I am talking about a constant current. So if I have a constant current, I can produce a magnetostatic situation. Or you come to the important conclusion that individual moving charges cannot produce magnetostatics. Individual moving charges cannot produce magnetostatics. Only a steady current can produce a magnetostatic situation. Then you will have a question. What kind of field can be set up by individual charges? For that, let us just work out this problem. Okay, this problem also gives you some understanding about the right-hand rule and all that. Okay, let's just try this problem. You have an alpha particle. You know what's an alpha particle, right? It's positively charged. You have an alpha particle. The alpha particle has a charge plus 2e. Plus 2e means Q is equal to 2 into 1.6 into 10 to the power of minus 19 coulomb. Okay. And it is moving in the positive x direction. So look at this picture here. This picture should be your guide. This is your x-axis. So this charge is moving along the positive x-axis direction with a velocity v. And you're taking a snapshot. You're taking a snapshot. Oh, there is a thunder. At that instant of time, this charge is, let us say, at the origin. I kept telling the position vector of a point with respect to the origin, and the origin is your moving charge. So let this be the origin at this instant of time. This is your x-axis, this is your y-axis, this is your z-axis. Okay. Now, what are you supposed to do? This charge is moving with a velocity equal to 0.05 into the speed of light. C is the speed of light. What is the speed of light, anyone? 3 into 10 to the power of? 8 meter per second. Okay. So that's the velocity with which it is moving, and it is moving along the x-axis. So I can simply say that my v vector is 0.005 c along the I cap direction meter per second. I'm writing it as a vector. Okay. Now, you're supposed to find out what is the magnetic field because of this charge at a point P1. At a point P1. This is my point P1. And where is my P1 located? My P1 is lying on the positive z-axis. And the coordinates of the point P1 are 0, 0, 2 centimeter or 0.02 meter. 0, 0, 0.02 meter or 2 centimeter. This is the coordinate of that point. And you're supposed to find out what is the magnetic field at this point. Let the magnetic field be B1 and you have to find out the magnitude and direction. Okay. So first of all, let us write the R vector. How do I write the R vector for the point P? Because I am interested in finding out the charge, the magnetic field at the point P1 with respect to the charge. So that's my R vector. I'll call it R1. Because it's P1, I'll call it R1. So what is my R1 vector, anyone? In terms of I, J, K? It's parallel to the positive Z axis. So I will write it as 0.02 meter or 2 centimeter along the K cap direction meter. Okay. Now I want to what is the next thing I need to do? I want to find out the magnetic field. So the magnetic field is going to be mu naught by 4 pi. Then what should I write? Q into, anyone? V cross R by R square. V cross R by R square. Okay, so substitute mu naught is 4 pi into 10 to the power of minus 7 divided by 4 pi. Then what is charge? Charge is 2 into 1.6 into 10 to the power of minus 19. Then into V cross R. What is I cross K? What will be I cross K? V cross R is I cross K. What is I cross K? Minus J. Minus J. So it's going to be 0.005 C into 0.02 along the minus K cap direction. Then of course divided by R square. R is 0.02, so 0.0 square. If I do all this, what is the answer I will get? Let me see. One sec, let me just. Okay, so I went up to some other page. One sec. Yeah, the answer that I will get will be 1.2. The magnetic field that I'm going to get is going to be 1.2 into 10 to the power of minus 16 Tesla and along the K cap, minus K cap direction. It's going to be along the minus K cap direction. In Tesla. So now let us see whether our cross product, whatever, if I have to ask you to draw a diagram, how will you put an arrow here? How will you put an arrow at the point P? It has to be perpendicular to R vector. It has to be perpendicular to V vector. Okay. Therefore, I may put it this way. Sorry. I may put an arrow this way or this way. Which is correct? Anyone? To the left or right? You see here, that will be perpendicular to R1. It will be perpendicular to V also. So can you tell me which one it will be? V cross R will be? Or tell me it will be along minus Y or plus Y direction. Answer is there. Minus K means what? Oh, just listen. Minus K means it is along the minus Y direction. So that's going to be your B1 vector. So that's going to be your B1 vector. Okay. Now the next part of the problem is find the magnetic field at a point P2. find the magnetic field at a point P2. And where is P2? P2 is having coordinate 0, 2, 0. 0, 2, 0. Where will that be? 0, 2, 0. Okay? The same thing you have to do. You have to do the same thing. Only thing is, you will write R2 instead of R1 and you will write 0.02 J. 0.02 J you will write. And you will, when you do the problem, you're going to get your B2 like this. Your B2 is going to be like this. Cha, what am I doing? This is your B2. And you're going to see that B1 and B2 will have the same value. 1.2 into 10 to the power of minus 16 Tesla. The reason is the numbers are all the same. It's just 2 centimeter, same Q. Only thing is your points were different. Therefore, the cross product will be different. And if you look at this, you are also going to realize that, okay, you can draw an imaginary circle. You can actually draw an imaginary circle around the x-axis. Around the x-axis, you can actually draw an imaginary circle, and these two are actually tangential to that circle and given by the right hand rule. B1 and B2 are points lying on a circle. They are lying on a circle of radius 2 centimeter. Therefore, the magnetic field is going to have the same value on that circle, and you're going to see that the direction is given by the right hand rule. So all these things can be studied in this one single problem. Okay. Now there is also a second part of the problem. The second part of the problem is, what is the magnetic field at a point P3? P3 is going to be just a random point. You have to find out what is the magnetic field at a point P3. So P3 is going to have coordinates 1, 1, 1. 1, 1, 1. So somebody should help me do that problem. So P3 is going to have coordinates 0.01, 0.01, 0.01. Just in case you're wondering why I'm writing 0.01, I'm converting centimeter into meter. Okay. So I can actually write my R vector. My R vector will be 0.01 I cap plus 0.01 j cap plus 0.01 k cap. And what is my velocity? Velocity is not changing. Velocity is still the same. It's going to be what did I say is the velocity? Velocity is 0.005 times the speed of light. Point 0.005 the times of the speed of light, and it is along the I cap direction. So use the same formula. Okay, V cross R you can do. V cross R you can do. The problem is being done in the book by the author in a slightly different way. Okay, he's trying to find out this angle phi, and he says that angle is 54.7. That is complicated. Don't go with this method. Don't go with this method. Instead, just go with what I'm saying. This will be easier. Just a cross product. And then in the denominator, you're going to have an R square. What will be that R square? This is R3. So what will be R3 square? R3 square is going to be simply 0.01 whole square plus 0.01 whole square plus 0.01 whole square. The magnitude of the vector squared. That's why I have not put the under root. So just substitute these things into this particular equation. Mu naught by 4 pi you already know. You know Q. Then don't do this. Instead just write mu naught by 4 pi Q V cross R by R cube you do. By R cube you do. Okay, so R cube means what? This will become under root So cube, if you have to do, it's going to be 0.01 whole square plus point. So 3 times you have to do that. Then under root and then cube. So 3/2. So put everything into that formula, you'll get your answer. This will be an easier way of doing this problem rather than what the author is doing. And look at the answer you're going to get. You're going to get 1.3 into 10 to the power of minus 16 Tesla. This is actually the important point of the chapter. 1.3 into 10 to the power of minus 16. The previous one also, we found 10 to the power of minus 16 Tesla. Believe me, this is a problem you can do mathematically. You can take a pen, you can take a calculator, you can do it. But can you do it in a lab means the answer is unfortunately 0. You cannot do it. Because on Earth, so far, there is no instrument which can measure this magnetic field. This magnetic field, 10 to the power of minus 16 Tesla, is very small. It cannot be measured. Okay? Or what we are trying to tell is, in real situation, you never try to create magnetic field by using single moving charges. Because the magnetic field that is obtained from single moving charges will be so small that it is of no use. You can't even measure it. Then the next question is, if that is the case, why the hell did we spend half an hour and try to learn about it? Will be your question. Why did you waste our time? We have 2 tests tomorrow. We could have gone and studied that. Why did you make us do this? Will be your question. The reason is that it is very, very small. It is so small that it is around 10 orders of magnitude smaller than the Earth's magnetic field. I hope you remember the Earth's magnetic field, 10 to the power of minus 4 Tesla or 1 Gauss. It is much, much smaller than that. You cannot measure it at all. But still, magnetic field due to individual charges have a significance somewhere. Where is that? Let us see. If you're talking about R, in this problem, our R was centimeter, 2 centimeter, 1 centimeter. It was centimeters. Instead, think of what will happen if R is nanometer. If R is of the order of 10 to the power of minus 12 meter or 10 to the power of minus 9 meter. Okay, then what will happen? Then look at this. In the denominator of the equation, if you have 10 to the power of minus 12 and you square it, when it goes to the numerator, what will you get? 10 to the power of minus 12 in the denominator, you square it, and if it goes to the numerator, what will you get? 10 to the power of?
24.
Plus 24. Plus 24 Tesla. That's a big, big magnetic field. That's a big, big magnetic field. So it's not something that you can neglect. So what do you finally conclude? You conclude that the magnetic field, because of these individual charges, will become independent when you're talking of atomic scales. When you're talking about inside the atom, when you're talking about the interaction between an electron and the proton or the nucleus, or when you're talking about 2 electrons interacting with each other, in those situations, the magnetic field becomes significant, it is large, and it is this magnetic field that you're able to see at the atomic level, which is responsible for magnetic properties of materials. You say some material is ferromagnetic, you say something is paramagnetic, something is antiferromagnetic. I'm sure you've studied all these words, okay? But all these things just come from this only. How a moving charge produces a magnetic field. And that magnetic field for a point which is very, very close to it, it is large. So it's able to influence another charge. And this influencing is what decides the magnetic properties. Okay, so with that I am winding up. And on 3rd, I think you have a test, right? Guys, on 3rd, you have a physics test. I hope you know that. Right. Please don't come for makeup. Please, for heaven's sake, don't come for makeup. Write your test the first time itself. Okay. Because always writing the test along with your friends actually is useful. I'm not saying that useful. Okay. Because that way you have friends around you who will discuss with you and if you are really academic. Okay. And next thing is, this time also, you're going to be divided into 2 groups. These batches are being made by the academics, or is it done by the individual faculty? Any idea? Slot 1 and 2. Do you know you are in which slot?
Yes, ma'am.
Who is making that slot? Was it sent by academics or should the faculty make it for different subjects?
Actually, for that each faculty, whoever's our faculty, they kept their name and those students in one batch, exactly mentioned.
Oh, like that?
For example, your
Ah.
name and Sri Ranjani ma'am's name was there for batch 1.
I don't think it is like that. I don't think it is like that.
It was
That means
mentioned like that.
I don't know. Let us see. Let us see. Okay, we don't have clarity on that. So be prepared for any batch. Be prepared for any batch. Okay, don't say I thought anyway. What is there? It's just 1 hour difference only. So be prepared for any of the batches. Madam will inform you. Is that fine? Because if what you are saying is right, then there will be unequal distribution of students. 2 sections means it's 160 and odd students in one batch and 80 in the other slot. I don't think it is like that. That is slightly unbelievable. Okay, whatever it is. So please don't go with your interpretation. You don't go with my interpretation also. Let us wait for clarity. Meanwhile, be prepared for both of these. Our exam is on 3rd. Tomorrow is 1st. We have 1 more class. Any doubts you are having, please come ask me day after tomorrow. Okay, so good day. Bye then.
Thank you.
Yeah, you can leave.